गुड इवनिंग एंड अ वेरी वार्म वेलकम टू द ब्लैक होल। हमेशा से ही मिथ्स को साइंस की ज़बान कहा जाता है, लेकिन इसे समझना हमेशा ही आसान नहीं होता। इमेजिन यू आर रीडिंग अ मैथ प्रॉब्लम एंड यू आर नॉट इंटायरली श्योर व्हाट इट्स आस्किंग यू टू डू। तो यकीन जाने आप अकेले नहीं हैं, मुझे भी नहीं आती कभी कभी समझ। टुडे वी आर गोइंग टू एक्सप्लोर अ वे ऑफ राइटिंग मैथ that's crystal clear, not just for humans, but for computers and AI engines too. The topic is formally writing mathematics for automatic reasoning. We are very grateful to our guest speaker, Dr. Mukhtarullah, who is sitting on my right. He is a professor and dean of engineering at FAST National University of Computer and Emerging Sciences. He holds a doctorate in systems biology from the University of Rostock, Germany. He has a research background in fields like computational biology, control systems, and artificial intelligence. He has published over 40 papers, supervised numerous PhD and MS students, and maintains collaboration with international universities. Please welcome Dr. Mukhtarullah.
Assalamu alaikum. Thank you for your kind introduction. So I have been giving lectures on this platform in the past. They were primarily in mathematical modeling and some fundamentals of math, but they were more focused on the traditional way of writing mathematics, which is prevalent in schools and colleges. What I have realized for the past few years, especially in today's age where you have access to all these AI tools, so you would expect to communicate in a better way with these tools. And then there is another issue of reading mathematical papers. So every now and then there is new research that gets published, and high quality publications, they require mathematical content. So the idea is formulated mathematically, and later on that algorithm is translated to some language, which you call programming languages. And there is this barrier. So naturally, the professionals are actually divided into two groups. There is a group whose members think only mathematically, and there is another group who they are comfortable coding. So this bridge has a problem, because the one who is doing math only, they take many pieces of math for granted, so it's understood for them. But they don't realize that someone outside that community has no idea about those so-called understood assumptions. So anyone who wants to make mathematics useful for today's technology, he or she must know how to write mathematics explicitly. So what I would request that after today's lecture, your approach to mathematics should change, whether you are a student or a teacher or a professional. So I'm sure you will be, in order to solve any problem, you will be learning math in some way, and then you will be writing as well. So if you make it compulsory on yourself that I will write mathematics in this particular way, it will give you two benefits. One, this way leaves no chance of any ambiguity. So it will make sure that you learn, you know what you are doing. And if you write mathematics in the traditional way, there is no guarantee that you understand what you are doing, because of those ambiguities. And the second and more important advantage is that once you are done with that part of your problem formulation, when you get to coding, or to some AI tool, when you look at your math, that will be very easy to translate, because it is already in a precise language. So that translation is much easier. So there will be no conceptual gap. So I think we need to get to the board. So if if part of the board is available, I will start with a few examples. And I would like to make it interactive. I think it doesn't matter how many topics we cover. What matters is the message. And I think you can convey the message with just a few examples. So it will not be an exhaustive search of literature. You just need to get familiarized with this way of writing, and then you will explore it yourself. Okay. And I also hope that you get this message across, because not everybody is here. So I will just start with examples where there is no ambiguity. So that will be a good starting point. So if I, for example, write something like, I have this symbol, you know what the symbol means, right? And let's say I write here 2, and I write here 2. So this is one of those examples where everybody can understand what is written down. There is no confusion. The interesting thing is that I know people who have problem even with this simple example. So if I ask you, everything in mathematics is an object. Yeah. So if you think of this whole thing I wrote as a single object, what will be the name of that object? Equation, right? Equation. That is the obvious answer. If you are talking to someone who is into logic, yeah, equation is a term favorite among mathematicians, because this is about mathematics and computing, and you cannot remove logic from this, yeah, merger. So if someone is into logic, what will be a better name for him or her? The same equation will be called? I'm sure you must have heard it. Yeah, they call it a statement. It is a statement. A statement is closer to the language of logic, or proposition. Why is that important? Yeah, this just a change of this name makes everything. It actually changes your clarity. So imagine you don't know these other two terms, yeah, proposition and statement. You only look at it as an equation. So my next question will be, what kind of equation? Because you can write many equations. So can you classify this equation? This is an equation of a certain kind. Now this answer becomes difficult when you look at it as an equation, right? But when you look at it as a statement, you have two kinds of statements, right? True statements, false statements. So now try to answer this question. Which kind of equation is this? In bracket, which kind of statement is this? So it is a true statement. And that same language is used in mathematics as well. So it is not just an equation, it is a true equation. Don't be shy, just say it. Okay? Now let me change something here. Now let's get back to ground zero. What will be your name for this object now? False equation. Now, believe me, I have asked this question many times, and I ask this to trick people. I'm not here to trick you. So I'm just giving you an example. When I ask this question in my class, and I'm not giving that background to them, you know, the majority give me a different answer. Can you guess that answer? I don't say anything about that statement, proposition. I just say, is this an equation? This is my question. And they say, it's not an equation. So they do not believe that this can be an equation. This is a perfectly legitimate equation, because what makes this equation is not its truth or falsehood. Yeah, we call it an equation because it follows a particular syntax. You have an equal sign and you have two things of the same type. It qualifies that it is an equation. Yeah? So I'm not into that topic yet, but you get, yeah? Now you know why clarity is important. So if you are not clear about what you are doing, then you will have all those, yeah, loopholes.
If we put a cross,
Yeah?
would that be a true statement, like 2 is not equal to 1? Or if we cross, they're equal?
Okay. Oh, yeah. This is a very good thing. So let's write another one. Yeah, because I don't want to destroy that. So let's say I write it in this way.
Yeah, this could,
What will be the object here?
No, that's a true statement.
this is a true.
This is a true statement. Yes. Yeah. But my question is different. This is an equation, right?
Yeah.
And this is also a statement. And this is false statement. So what you said that this is a true statement, so it is a statement, but is it an equation?
No, because we negate the equation. Right?
It's not an equation anymore. Because equation, to be called an equation, you need that equal sign. So just because it's true doesn't make it an equation, right? So what will be a name of this now?
The statement.
Statement है वो तो ये भी statement है ये भी statement है. But what is this? I want you to be very clear. So the problem is that we are doing math, but we cannot explain the math. So math becomes useless to the other disciplines only when you can talk about it, when you can write about it. This is actually an inequation. It's called inequation. Yeah, or inequality or disequation, whatever you have many names. Yeah, but can you now see the superiority of the language of logic? Logic has the same name for both. Statement. So the language of math is actually not very cool for these kinds of objects. I don't want to say that you should abandon that language. Mathematics is a reality. You will still be reading mathematical literature. But I think today it is very important that you are comfortable with both sides of the story. Yeah, because you cannot actually, in the past it was very easy and it was very comfortable. Now you cannot avoid. Mathematicians cannot avoid computing, and computing professionals cannot avoid mathematicians. So let's do something else here. What will be your name for this object now?
That's an algebraic equation.
No, yeah, you call it algebraic, but it's still an equation, right? Yeah, that x doesn't make it a non-equation. It is still an
This
equation.
is true if x is 0.
Yeah, but that question will come later. Yeah. So let's go step by step. Right? So we are clear. Everybody is clear that this is an equation. Okay, no confusion. Let's get to the language of logic. Is it a statement?
No, it's not a statement. It's an equation.
Yeah. No, in the previous cases we had objects that were equations as well as statements. So now this is still an equation, but can we call this a statement? Yeah. I don't expect an answer from everyone. Because here it's not about a question of your common sense. If you know the meaning of statement, only then you will be able to answer that. So let me actually remind you that when you call something a statement in the language of logic, it must be either true or false. There is no third possibility. Yeah. So if it is let's assume that it is a statement, which may or may not be wrong. If I call this a statement, then I must be able to tell without any confusion whether this is true or false. Can I do that? No, I can't do that. Right? So it means that even if you forget about this language, if you go back to the language of equations, this is an equation, but this is neither a true equation nor a false equation, because you cannot say that for certain, because you have no idea about x. Okay, and if you but if you want to call it a statement, that is wrong, right? So it means that logic will have a different name for this. By the way, if you want to classify it in the language of equation, true equation, false equation, this is called a conditionally true equation. Just remember, write it down somewhere. Conditionally true or conditionally false, because the value of x will determine whether it's true or false. In logic, you don't have that name. You cannot say, oh, it's a conditional statement. Yeah, because it is not a statement at all. So there the name for that is proposition. So you see, I see I used this word proposition before as well, but that was actually very loose. Yeah. A better word for this is a predicate. You must have heard that as well. Predicate. Yeah. Some people even call it a formula. So in some writings you will see formula, in some writings you will see predicate. This proposition is actually debatable because some people think that proposition is just another word for statement. Yeah. So there I would put a question mark. It depends on which author you are reading, but these two are clear: predicate and formula. Right? Is there any confusion so far? I think I tried to make it simple so that you know.
Preposition comes, first thing that comes to your mind is English language, where this preposition.
No, proposition. Proposition, not preposition. Proposition. Yeah, proposition. P-R-O-P-O. Yeah, you don't need to feel bad because I mean I don't expect every one of you to be. Yeah. Proposition. Okay. So, but now let's get to another question. That was only about terminology, right? Now there are more important things related to this equation. When I write this equation, how do I know that I have to look at this from that particular angle? Yeah. How do I know that I have to look at it from a language of logic? So this thing will be clearer if I do something like this. Yeah. And I'm sure you now the previous equation, there is only one value of x which will make that equation true. Yeah. For all other values it will be false. Okay. What about this equation? How do I know whether to treat this equation as a formula, yeah, which will be for each value of x it will be a statement, right? So I cannot call it a statement, but for a particular value of x it will be a statement which will be true or false depending on that value. But how do I know? Can you tell me that this same I would not call it an equation, this same piece of math is written down when you mean something else, and we will never call that an equation. You must be able to recall that.
So here x is a variable?
Yeah, x is variable, definitely.
But you have a value assigned to x, so...
Yeah, so you see, I think you got there. We write this also when we want to assign 1 to x. Then this will not be an equation.
It's not a variable?
Yeah. No, x is a variable to which you have assigned the value. So you are just naming. Yeah. So you don't want to write 1, and for this there is no point. But maybe this is a horrible number. Yeah. Do you know the speed of light? Right.
325.
That horrible. Yeah. I mean we write 3 to 10 to the 8. But this is not the actual way of writing down. Yeah? The actual value is not. Yeah, it's very horrible. Yeah, nobody wants to write that. Yeah, so we say, okay, let's give it a name. Yeah, and it's much easier to write C than to write that whole thing. So this is not an equation.
So it becomes a constant.
This is a definition. This is a definition. A definition. You cannot ask this question whether that is true or false, because that question does not arise. Yeah? You should not allow anyone to question this because you are naming it. C is a name for this thing. So this is not a statement. You cannot even say it's a true statement, right?
This already sounds like a shortcoming of the notation of math.
Yeah, you're right. So now we are getting there. Programmers have found a way of removing this confusion. What do? They use a different symbol. This is their way of getting around this problem. But the problem is you cannot use this symbol in mathematical writing because they have their own language and they cannot accept that you stick your nose in their business. They won't allow that. So you have to adjust yourself to their language. You cannot expect a discipline which is thousands and thousands of years old to adjust to modern technology. And this is not a good idea anyway. Maybe this is in Python. Maybe there are languages which I know languages, and they use that equal sign for this check. And for example, lean. Yeah, lean is a very actually it's a different kind of language. They use this. For this they will use this symbol, and for this purpose they will use this symbol, colon and equal. So then how to decide which language is superior? So that is not a way of solving problem. The problem is stick with the mathematical language, but do something to clarify it. Yeah. So we need to add some piece of information so that we make it clear what do we mean, yeah, without changing the symbol. So what will be your suggestion? Now I'm writing x is equal to 1, right? So what should I do to turn this? So maybe suggest something to turn this into an equation. Sorry, not an equation, to a statement. To a statement. So one way that maybe you are claiming that there is some value of x for which this equation will be true, right? But maybe you have another thing in mind, that this equation is true for all values of x. So we now already have to, so mathematics now and combined with logic has a symbol for that. So for some x, x equals 1. For all, so let me just write this. You say for some x, and you just write this as a qualification to this equation. Now this whole thing is a statement. Even though you have x, now can you now tell me, is this a true equation, true statement? Yeah, because you can find one value for which this is. So it is because of this sum that it is actually it is a true statement. Let's change this. I'll get to that mathematical symbol later because we have to go gradually. Yeah? So if I say for all x equals 1, this is definitely a false equation, right? And if I mean by this a definition, I'll write something else here, and you can actually help me there. What will be the best way of turning this into a definition? You have seen it. You have seen it. We typically write this. Let. Okay. So now I will write down what mathematicians have settled. Okay. So for these two, they still use this symbol, and I can now replace this thing. You must have seen this e written, yeah, flipped right to left. And there you will have to write the name of the variable. So it means that there is nothing special about x here. You can write y, you can write z. There is no superiority of x, y, or t. You can find whatever you want, but you need a symbol. Yeah? That symbol must be preceded by this symbol, and then you need to give it either a space or maybe a bracket, or just way. This is not multiplication, this is just a qualification, a shortcut for that thing. Yeah? And this thing is not multiplying x in any way, yeah? It's just a qualification. Yeah? So just like you say Dr. Mukhtar, so you don't say Dr. times Mukhtar. Yeah? So, okay, and for this you must have seen this upside down A, X, and now I want to test your guessing power, yeah? Whether you can make an educated guess. What do you think could be the reason of that E, that inverted, sorry, yeah, flipped E? That will become easy if you come up with an alternative way of writing this. So some people say for some x, some people say there exists a value of x. So exists that E. So this will remind you that it exists. And all, yeah, flipped on. So that is actually a tip for remembering this, right? And here, some people just write it this way, but I have seen people, this is not very cool, yeah? The reason this is not cool is that it is English and you cannot impose English on everyone. So mathematics should be universal and no language should have any superiority, right? So many people have actually settled down to this symbol. Yeah? Yeah. You can see in literature some people just write this equal sign with a triangle on top of it. Yeah? And I have even seen this thing. 3 lines. You must have seen, yeah. One last, I think there are no others. Just DE, F. This community, they want to make it clear that you see DEF there, and then for this they will have a question mark. So is it equal? Yeah, but I think that's too much. Yeah, so don't do that. This is better, right? So you see, just by writing that qualification. So okay, now I'm calling it qualification, yeah, condition, but we need a precise term which everybody agrees, yeah, because I'm not the creator of math. So we need to, these are standard symbols, yeah. So we need a standard name for whatever you write here, yeah. That name is called a quantifier. So this is this is also a quantifier, right? This is called, because of that existence, this is called an existential quantifier, because you need to distinguish between this quantifier and that quantifier. So this is the existential quantifier, and this is the, can you guess the name? Universal, yeah. This is the advantage of having people from the domain, yeah, universal. Because I was struggling to recall that. Yeah? So this also means that you can never trust your memory, right? So then you have to thank your colleagues for that. Universal quantifier and existential quantifier, and try to say it out loud, yeah, because this is what I learned from a professor who visited our group. He said that if you say something loud, it's very easy to remember, yeah. So you don't have to shout. Okay, I think this is, if there's any question, I would like to receive those questions now, because I'm sure the next thing is a bit heavy. So are we fine so far? Yes?
Just a comment. If someone is confused about why we flip the E sideways and the A upside down, they can ask me.
They can ask you? Oh, okay. Yeah. Yeah, if there is any confusion. But if you just write E and A, then, yeah, then it will be E times X or EX. Yeah? So there are many ways to confuse that with something else, right? So let's get rid of this now. And we now need to pick on that quantifier, right? But let me write down another thing. And this will now create a series of questions. So let's write something like this. I write 2x plus 1. So the first question, what will be your name for this object? Expression, yeah. I just love that because normally I don't get that answer. Yeah? So it means that you are now into this, to this new way of thinking. Can you guess a common misconception about this? Yeah, that is very stupid, but there is no shortage of stupid people on this planet, so I can expect that. So a little less stupid. So what will they call it? Many people think of it as a function, right? Because this gives the impression that x is a placeholder, right? And the expression, this thing will ask me to give a value, right? And it looks like that. Give me x and I'll give you 2x plus 1. This looks like a function, right? That's what function does. A function is a computational box which asks you for an input, and that input will have a name. So here the name looks like x, and in return you get a value. So it is stupid, but it is not that stupid. Yeah? So now it begs the question, we need some quantifier to clarify that this is a function. You don't need any quantification or qualification for an expression because it's very clear. Yeah? Even if it is an expression, right, still one thing is missing here, because we all here are humans, and humans are intelligent, so we automatically, do you know what is missing? Even if I agree that it is an expression, one thing is missing here. We said nothing about x. This x could be a number, this x could be a matrix, yeah? And this x could be a function as well. This x could be, how many of you are familiar with the derivative? Yeah, so we have some people, yeah? What do we write for derivative? D, right? So if I replace this x with d, this is a perfect expression. This means that first differentiate something whenever you write something there, yeah? Then twice, and then add 1. Yeah? So how to remove that confusion? So even if it is an expression, it is an expression. So there are two ways of writing it. One way is to write the type. So I will say colon. So now this is a very standard symbol in mathematics which is aware of these types, yeah? Because there are two groups of mathematicians, yeah? Those who don't care, they say, okay, we write for experts and they know what I'm writing. And those who are like me, who care about the common audience and who care about computing as well. So when you are writing code, you can't just bring x, you have to declare the type. Yeah? So when you say int x, you are telling the compiler that it is an integer, and it is not a real number, or it is not something like that. So in math, you don't no mathematician will agree with this thing. Yeah? Again, C++, Java, all these things. Yeah? So they just write a colon, and there you write the name of the type. And the names of the types in mathematics, so if you want this to be an integer, you will just write this symbol. Yeah? So that one thing clarifies that x. Now there is no way that, there is still a confusion about x. This only solves half of the problem. Can someone guess that this is not enough? Can you think of a value of x where x will not be an integer and 2x plus 1 will be an integer? So my claim is that this settles the issue that x must be an integer, right? Because this expression must be of type integer. But I want you to be more careful. There is a value of x, for example, if x is 3, 2 times 3 plus 1 is an integer. So x can be 3. So what one way of thinking about this, that x is any integer, right? X is any integer. So this is an expression which can only evaluate to an integer. But x can be 1/2, for example. Yeah, but this notation is saying nothing about x. This is only saying about 2x plus 1. So do you see the problem? That we have solved the problem only partly. We need to write something that like that existential or that universal quantifier. Yeah, this is actually, I also liked the word qualifier, but they call it quantifier. So you cannot blame me for that. Yeah, we have to live with that language. Qualifier is a better name. Yeah. So, but yeah. So what should we? It means that this does not settle the issue. Yeah, there are some expressions where this is enough. So, for example, if this 2 was not there, then this would have been enough. Now I don't need to say anything about x. So you can imagine a parser. You know parser? I mean, which actually tries to read this and make sense of it. So somebody can write a rule that yeah, if you can figure out. So here I can figure out that x, there is no way x can be a non-integer. But with that too, there is a problem. So it means that we need to find a way, and for that now I'll write something here. And this problem was solved by Bertrand Russell. Yeah, is that a correct way of pronouncing it? Because I'm not the best person on this topic. Yeah, I think it's, forgive me for spelling. So he came up with this quantifier, right? And he called it the description operator or description quantifier. And by the way, this is I, right? There is a Greek letter called iota. How do you write that? If you write it without this dot, this is called iota. Iota, right? And there is something very unfortunate. You know this thing? We call this iota. This is not iota. Have you ever seen this thing? This is I. Actually, we use the symbol I. And I is not iota. I is the English letter I. So which begs the question, what is the correct name for this object? It is not iota. So what is it? The imaginary unit. Yeah. So yeah, try to use the correct name. It is the. Yeah, people call it iota. That doesn't mean that it's correct.
But why do they call it?
Yeah, because they don't know the fact.
Generally across the world, everyone.
No, not everyone. Not everyone.
It was the case in our
YouTube is full of stupid people, right? And the more stupidity, the more, I mean, things become actually widespread just because of these people. And it's much easier to actually fall into that trap. Iota has nothing to do with this thing, yeah? Period.
And because iota has some other.
Iota is coming here. The topic I am actually, iota is this thing.
The problem arises because it has some other denotation.
No, that's not a reason. It never was iota. Yeah, somebody made a mistake, and we have to live with that mistake now, right? Another thing, I'll tell you another thing. Forget about this thing. So we are clear that this is what? This is I, and I is for the imaginary. Imaginary is an English word. No iota there, right? Try to search imaginary in Greek, and you will. I don't believe that you will see iota there, right? Okay. Now let's get back to that widespread thing. Yeah, just because many people say something doesn't make it correct. How do you pronounce this whole thing? Yeah, under root minus 1. Wrong. Let's write this down. Yeah, under root What is root? Square root, cube root. So root is the answer here. The answer you get is the root. Yeah? So if I do this with 9, what do I get? 3 is the root. 3 is the root. So if you say under root, that thing should be on top of 3, not on top of n. Do you get the point? Root is the answer. Yeah? So the name of this symbol is actually radical. So it is 9 under the radical, not under the root. Now how many people say radical? Yeah. So the purpose of this talk is to make everything not only clear but also correct.
Can you try to explain to us what is exactly wrong with calling it root?
I told you this is the root. And if you say under root, then this symbol has to be on top of that, and that would be wrong. Under root. Right? Under root is a Bollywood thing, right? And you know how proliferating Bollywood can be. So that is totally, and I can give you many examples, but I don't want to give more examples because the purpose of this lecture is something else. Yeah. So I would highly encourage you to collect all these incorrect ways of pronouncing things. I'll just give one related example and then we are done because this was not the agenda. Let me ask you another question. Right? So what is 3 here? What is the name of 3 here? Huh? No, how do you say this left hand side?
2 की power 3.
2? No, let's make it clear because I don't want to bring cube here, yeah? I want to make sure that the problem is addressed, right? And cube and square actually hides the problem under the rug, yeah? So I don't want that to happen. What is 4 here? Power, yeah? 99.9% people say power. Wrong. This is the power. This is the 4th power of 2. Yeah? What is the first power of 2? What is the first power of 2? What is the no, first power is 2. 1 is the 0th power, right? 1 is the 0th power, 2 is the first power, 4 is the second power, so 16 is the 4th power.
How is it definitionally wrong though? So when we say 2 to the power 4, don't we mean
Yeah, but this is the power, this is not the power.
exactly?
No, you should say 2 to the 4th power.
Exactly. So everyone says 2 to the 4th power.
Yeah, but that does not make 4 the power. Power is still 16. You see the point? Yeah, 2 to the 4th power, but 4 is not the power. This is very important. 4 is the exponent or index. Index, exponent, order. You will see these names. Power is nowhere in that list. And now just because YouTubers call it power doesn't make it true. It's still wrong. Even if you find it in 1 million books, it is still wrong. Because something which is wrong, it will remain wrong regardless of the number of books you see. Yeah? So what is the correct way of saying that again? 2 raised to the, not power 4, 4th power. Yeah? Because when you say power 4, you are calling 4 the power. 4 is not the power. 16 is the power. Which power? 4th power. Yeah? So, yeah, and there, let's complete this now. How do you go back from 16 to 2? It is the 4th root of 16. 2 is the root. It is the, no under root. Yeah? 2 is the 4th root of 16. 4 is the second root or square root of 16. And if you want to say that 16 under the रेडिकल साइन, या अंडर रूट को बिल्कुल डंप करे, वो है ही नहीं, एग्जिस्ट नहीं करता, ठीक है. सो लेट्स गेट बैक टू द एक्चुअल टॉपिक. या why did we start this thing, by the way? Because this is a distraction which iota. Yeah, so iota is actually has nothing to do with that thing that is the imaginary unit. Yeah, and now how will you say that? Imaginary unit, and if you want to say that, -1 square rooted, yeah, okay, or square root of -1. Okay, so now let's get back to the original question. What was that? I have an expression, and one thing is very clear, that this expression is a numeric expression, which means that it will evaluate to a number. I still don't know that number, but yeah, just because I don't know, I'll tell you the wrong reason. People who are calling this a function, they have a reason that because I don't know x, it is begging for the value of x, so that makes it a function. That is wrong. I am using x because I don't know the value. It is still a number, right? So if this is still a number, this whole thing will still be a number, though an unknown number. So now I need to write something, and that iota comes here. Actually, it is not iota. I mentioned iota because what Russell did was something related to iota. There is another symbol. Iota is written in this way, right? Without an I. What if I turn this upside down and then right to left? So upside down and right to left. How will it look like? Yeah. So you flipped it both upside down and right left. This is a valid character, and it's called tangent iota. What? Tangent iota. This tangent iota is what that guy Bertrand Russell invented to solve this problem. And the name of this is the description operator. So this tangent iota, this tangent iota is now our quantifier. Yeah? Instead of that existential or that universal quantifier. And what is the symbol you want to use here? And you must be asking, why do I need to write this symbol? Isn't it clear that there is a variable? So by the way, why don't we simply write this thing? Why do we write the name of that symbol? Anyone who can guess that? I mean, it should be clear. If I write this, should be enough. And I know I'm writing that x, let's say x equals 1, yeah, or x equals 1. So why do I need to write the x there? Because that equation or that formula or that expression may have other symbols like y. So what if for example x is equal to y, right? So that y may be a name for something fixed. Maybe before that you have done let y equals 3. So now you are using y just as a name for a fixed object, no variable. So this gives us another thing. When we say variable, we should be very careful, because here y is just a name. So it's better to call it an unknown, because you don't know the value. Someone who defined it does. Yeah. So in that case, in this equation, I need to make it clear that my claim is for some x, not for some y. So that is mandatory, right? So similarly, because this expression can have other objects as well in that manner, so I have to write down tangent iota, which is the description operator, followed by the symbol you use, and then it's up to you whether you put a dot or a bracket. Now this is definitely an expression, but one thing must be clear, I need to tell the type of x. So if you intend x to be an integer, you must write now this is an expression which requires x to be an integer. Can somebody guess why don't we write it in this way? What do you think will be the difference between these two? Doesn't this tell the same thing? Many people use this, by the way. And same can be here. What if you want x to be, for example, integer? So what do? Because just saying for all is not enough. You have to tell the type as well. Yeah? For all and exist doesn't tell anything about the type. Although many people don't care about this, but because you are now into this new frame, in the beginning I asked you about statements, right? A statement which is either true or false. And when you don't know it, it becomes a proposition or a predicate or something like that. So this looks more like a formula where the value of x will tell whether it's true or false. And this is actually a declaration. You are declaring that x must be of type int. So there is no question about this being false or true. Do you see it? Like in that language, like in C++ or Java or where, you introduce a variable, and what do you do there? Int x. This is not the same as writing, because this may be false. What if x is not an integer? This statement will be false. But here, there is no question about that. That is not even a statement. That is a declaration. Declaration, right? So now we have the third quantifier. We started with existential quantifier, universal quantifier, and now this description quantifier to clarify that it is an expression, and we also clarify the type of variable. Once you do that, it doesn't, you don't need anything here, because that is clear. 2x plus 1 will be an integer. Is this clear? Now, one last thing. What if my intention of writing this 2x plus 1 is not an expression, but a function? Yeah. So let's say what I have in mind, I won't remove that, right? Let's say I have a function box in mind. You can think of a function as a box which takes an input and it gives you an output, right? So let's say this function requires x and it gives me. So now this is a function. So what should I write here to turn this into a function? That has also been solved. And that is a problem which another guy solved. His name was Alonzo Church. I'm sure you have heard this name. Alonzo. Have you heard Church Turing? Yeah. Church Turing, Turing machine, and then Church Turing, I would say theorem or something like that. So he invented an operator or a quantifier which will turn this into a function. Let me tell you, here it's not very important. Yeah? Here the purpose of this is to actually remove the confusion with function and to clarify the type. But here, if I want this 2x plus 1, of course, I will never be able to turn this into a function, but I'll write something, and that whole thing will be a function, right? And for that, the quantifier is called lambda. And because lambda and this turned iota, you might be needing these symbols for other purposes. Sometimes I need iota or turned iota to just name something else. So there, the convention in logicians is that these italics, these Greek letters, they can be written in the italic format or straight upright, right? So the convention is that these quantifiers, they must be written down straight upright, and you must find a way of actually find how to write that. Yeah. So it will not be italic but upright. So lambda, and you can now guess what should it follow? The symbol. Yeah. So for example, if I have a y there, and if I have an x here, it will be a function of x, where you assume y to be a fixed object. Y cannot be free here. Y must be a fixed object. So that's why I didn't write that down. Yeah? So now this is still an expression, but this whole thing is a, yeah, you know it, say it, it's a function. Yeah? So what we did today, we learned 4 quantifiers: existential, universal. They are for formulas, logical formulas, or Boolean, or whatever you call it. And these are for algebraic expressions. Can you see the advantage of this way of writing down? Because when you make it mandatory upon yourself to write this, your clarity actually increases, and then later on you know how to implement this. So for example, if you want to implement this as a function, you know that this lambda x will require me to write some. What do you do in programming for this? Of course, you don't write lambda, but what do you do there? How will I do that, for example, in let's say in Python?
Y is equals to 2 static x plus 1.
Do you think this will be enough? I don't think this will solve the problem, right? In Python, you must write something. I think it's def or what? def? Yeah, def or something. But my point is that when you keep writing this, you will have this in mind that I will have some keyword in that particular language for this. You can't just turn an expression magically into a function. Yeah. Because I'm following lean these days. In lean, you have to write fun. Yeah? And MATLAB, it is full name function, function. Yeah? All these different keywords are just there to realize this lambda. And by the way, Python has a direct implementation of lambda as well. Other languages don't. So maybe someone who has used lambda, I'll now write down that syntax. Yeah? Those who are into Python, they must recognize this. Because the unfortunate thing about lambda is it doesn't recognize these symbols. Julia and Lean, they do allow you to use these symbols. So lambda, and maybe Imran, you can help me here. The good thing about this lambda is that you don't need to give a name.
And you can write x.
Normally you have to write f of x equals. Normally what you do? So now you are using f as a name. What if you need that f for some other purpose? So the good thing about this is that you don't need any name. You just need a quantifier. So lambda, and I think it's x, and maybe it's a colon or something. And then 2x plus 1, yeah. It is something like that. And remember, let's put this in a bracket in Python. Let's say you do that. And if there is anything wrong, you will figure it out yourself. You are more professional than me. And similarly, let's write this down in a bracket. This is now a function, even though you don't have a name for it like sine, cosine, or log, but it is a function. Yeah? Which means just like you know sine, yeah, and log. What can you do? You can just apply that to any number. Yeah. So you can apply it, for example, to 3. You can apply this to 3. I can apply this to 3. No, don't. So tell me, what will I get out of this? What will I get out of this? 7, yeah, 2 times 3 plus 7. And exactly that here. You don't need any operator, no star, nothing, because it is now a function object which you can apply to other objects, right? So, yeah, because this lecture is about clarity, this actually reminds me something else here. What if I replace this with 30? Who has calculator? I want you to work this out. What is sine 30? 1 by 2. Wrong. Wrong. You know why? Because when you write 30, who told you that it will be degrees? Who told you that? So that means that we need a universal convention. The universal convention is that when you just see a number with no other information, it will be radian. And you cannot decide that. It has been decided already. So if you want this to be degrees, you have to explicitly. There is no choice. This is not a choice. This is not, you don't say, oh, I forgot it, right? So if you mean 30 degrees means 30 degrees. 30 degrees doesn't mean 30. So sine 90 is, don't say 1, because 90 means 90 radians, right? So I think I will now do not underestimate this description operator. I think I missed something here. Now I just realized that this quantification, right? What did I write? And this will now give you a limitation of humans. Yeah, they think they are smart, but I completely messed up something here. This is not what this turned iota or description operator is for. Here, the only thing we need to clarify the expression, because this is an expression, you don't need anything. You only need to mention the type. So what you need to do, x. That's enough. You don't need anything else, right? Or maybe you can say for, right? What? For or something like that. So now let's get to the actual turned iota, which I just now by chance recalled. Yeah. So let's say that you write that description operator or turned iota. Then you write the symbol. What you need to do is that you have to follow it by a logical formula. So what you are doing is that rather than defining something directly, if I tell you, for example, if I now ask you, try to define this, so what will you do? The best you can do is to take your calculator and press that button. But you are using some solution by someone else, right? So how will you define this thing? What will be your definition? You'll not tell me the square root of 2, but that is just another name. A definition requires, so this can only be defined indirectly. So I will say that it is this operator followed by x such that, so now I can put a dot or anything, and now I have to write a condition which x must satisfy before this expression describes this thing. So can you suggest me a condition here? What must x satisfy? X squared must be equal to 2, right? So this whole expression is 2 square rooted. There is just one thing missing which I want you to actually figure out. We have to specify the type of x. So what is the type of x here? If you solve this equation, what are the two solutions? This is one solution, and the other is? We only have this in mind. So if I write this thing, this expression will be undefined because this description operator requires a unique answer. And this condition does not give me a. So what should I do to make it unique and only this one? That means that just writing x is not enough. I have to write the type. The type of x cannot be integers, right? It must be real, right? But that negative 2 square rooted is also real. So how to rule that out? No, I just need to write plus here. You write something to make sure that x is required to be real by its very makeup, and now you are writing a condition. So this whole expression, so now this is the actual use of that description operator. What I did before was actually some convolution in my mind, yeah. So you can never trust humans, yeah, no matter how much they claim to be, yeah, fresh or something like that.
How much do we have to distrust it?
Yeah, hopefully this, yeah, but you can always verify, right? So this is, so the description operator is followed by a symbol, and that symbol you must specify the type, then you must specify the condition, and now this whole expression, this is now an expression. This expression is now the definition of what? Here I have defined the square root of 2 in a crystal clear manner without any confusion. You know why this? If you write it in this way and you are asked to implement the square root function, this will give you a lot of hints to come up with an algorithm. Yeah, maybe a search algorithm or something like that. But if you are used to just pressing a button, you cannot expect your brain to come up with algorithms. Sorry. Pressing buttons don't give you algorithms. You need that mathematical clarity, and that clarity doesn't come by pressing buttons or copying and pasting things. So what if I don't do this? I want you to be able to write down the value of this expression if I don't do this. In the previous case, this was 2 square rooted, right? And just to help you, if I write minus, then it will be minus 2 square rooted, the second one. So now you also have a free definition for minus square rooted. But what if I don't do that? This will evaluate to? No, that's the problem. That is a very instructive way of thinking about it, but we must not forget that it's not me and you to decide. Russell decided this to be a unique description. Yeah? So by definition of terned iota, this must give you one answer. So now, what is the value of this expression? Actually, you know it, but you are not telling me the name. If you implement this, let's say you implement this in some language. You write a function, and you write this logic inside that function. And when you run it, what will you get out of that? Let me try to write this down, yeah? So let's say I write, let's say, fun function, yeah? And f, and let's say it doesn't require any inputs, and I just say n, and I just apply this condition, yeah? If, sorry, yeah, sorry, x, yeah? If x squared is 2, return, yeah, something, yeah? Return some symbol, and then you say end. Now, if you run this code, because this condition is never met, it will not give you any value. So this expression cannot give you any value. It doesn't give you anything, so it is actually nothing. So undefined is just a mathematical name for that. Why I took so long to describe this? When you ask someone in school what is undefined, they don't know the definition of undefined. They just have examples. So they will say 0 by 0 and 1 by 0, as if they are the only two ways of being undefined. Undefined means not defined. Not defined means that you do not have a unique value. Yeah? So this is simply undefined. So if I just want to express this, one way is to say that it is equal to. Now the problem with this is that when you write undefined, somebody can actually misunderstand that undefined as a name for something, yeah? And then you are again into trouble. So what should we do to make it clear that it is undefined and it has no value? Right? I'll now help you. You already know one object in mathematics which represents nothing, but not directly, indirectly. What is that object? The empty set, right? Empty set, right? So your first guess will be that this whole thing as a single expression equals. This is not the correct solution, but at least you are halfway through. Now we just need to change this to make it correct. And I want you to figure that out. You can do that. I was actually listening to a speaker from Mexico, and he wanted his audience to be present. So he said, "Come on, you can do it." So you can do it. It should be a member. And you know, only nothing is a member of that set. So you don't need to say N-O-T-H-I-N-G, because that nothing who is not from English, he will think of it as a name. This is a mathematical universal symbol. No one, I mean, anyone who doesn't know this meaning should not be doing math anyway, right? So that you are safe, right? They should be kept away from math. I think this is the end. So there are other examples as well, but if I had one example, and only if you guys want to know that this method can be used to define. I wouldn't say define, but to test. You can also say define, yeah. To test whether a number is prime or not. So maybe you can try this, yeah. That will be a homework. Yeah. That was the last example for this lecture. But I think the too much information was given to you, so let's stop it there. Now I can receive questions.
हेलो सर आपने इन अनडिफाइंड के बारे में बताया. कुछ लोग 1 डिवाइडेड बाई 0 को इन्फिनिटी कहते हैं, तो
That is one type of undefined.
ओके.
So yeah, it's a good question. Let me just answer that. This is the most general. So another way for this is that this value does not exist. Yeah? There is no such number. Yeah. So when you say 1 divided by 0, I can safely say that it belongs to nothing, because there is no value. You know why I am saying that? Let's try to address this thing in this way. We already know a way. So how can I write 1 divided by 0. So now let's write a definition of what? Of 1 divided by 0. Can you now tell me? What should I do here? So I will start with the description operator, tan iota. X real, I hope that it is real, right? And what do I do? You know what do you have in mind? 1 over 0 equals x. 1 over 0. So try to solve this equation. 1 over 0 equals x. So this means that 0 times x must equal 1. So that condition is, yeah, this must be followed by the condition. What is the condition? Now give me a value of x which makes this equation true. Is there a value? There is no value. Calling it infinity doesn't solve the problem, yeah? So don't go for fancy names. Why people use infinity? It is not because this is false, this is still true. So this is still not a value. The reason it is called infinity is that you want to distinguish between two types of, there are many ways of getting into this. So this is one way, but I'll now give you another way, right?
Sir,
Yeah.
if it 1 over 0,
Hmm?
giving the name of infinity, that appeals to common sense also. Denominator getting near 0
Yeah.
is making that object
You
very large.
what you are describing is the limit.
Yes.
We are not describing the limit. We are describing the value.
Yes, but going towards 0 for the
Yeah, yeah,
so that automatically with our general
Yeah, yeah.
perception
yeah.
converts that side or that term very large,
yeah.
large.
Yeah, yeah,
So
yeah.
that notion in common sense.
But it's still not a number. No matter how large, it is not a number. There is no number which makes this equation true. You know what you said actually is now a divide between engineers and mathematicians. I am an engineer and I'm also inclined towards that. Engineers and computer scientists, they both fall into this trap. We think of infinity as a very large number. Even if you spend 1 trillion 1 trillion years, raised to 1 trillion years, you will still not get that number. So pure mathematics says that there is no number. Yeah? The reason people use that symbol is another one, I'll tell you. It is because of the limits. If we want to increase something and we want to say, I will keep increasing this, and I will not stop. I will not stop is a very long way of describing that thing. Yeah? So I say, now I'm writing down limit, right? And I say x is very large and no boundary. Who is stupid enough to write that thing? So mathematicians don't try to write these long sentences. What they do? They
Limit
invented,
tends to.
yeah.
Yes.
This is still not a number.
Yes.
That is just a short way of avoiding that long thing. As an object, it is, so that is why this symbol, it is still an object, but it is not a number. Right? Yes.
Okay, sir. Pardon my insistence on this, just limit.
Yeah.
As you know, everything, even with the eye of an engineer,
Yeah.
everything we look at, everything we measure, everything we weight, that is approximation.
Yes. But math is not an
So,
approximation. Math is not an approximation.
it is an approximation. So to represent mathematically or logically an approximation, the concept of limits gives us a reasonable answer.
Actually, let me tell you, if I write here x, right? And if I write here x, and if I write here x, what will be my answer? Tell me. I'm getting to your point now.
Of course, under this limit condition, it is infinity. Yes.
Yeah, but what does it mean? It doesn't mean that infinity is a number. That what I'm trying to do is to clarify the meaning. What it means is that just like you are not stopping, this value will also not stop. So let's say if I divide this by 10, just like you don't want to stop, x by 10 won't stop either. But that does not make it a number. Yeah, you can waste the rest of your life and then the next generation and then the next generation. The point is to clarify the nature of this thing. Yeah, what you refer to is actually applied math. In applied math, engineers, computer scientists, computational, we do that a lot of time. But that is the thing. So, but let's get to this. Yeah, let's change this to 0 by 0, and I'll now tell you why we need this symbol. Yeah, right. So actually, this is, you can think of this as, this is perfectly okay, because I've just given this expression a name. Giving it a name is not a claim that it is a number. Yeah? Some people say, oh, this is wrong. Why do you do that? No. I'm just giving this a name. So there are three representations. This is one representation. This is another representation which makes it clear. And this is just another representation. They are all tell me the same thing, that there is no such thing. But how to distinguish between that no such thing and another way in which that no such thing arises? And now tell me, what if I replace this with 0? Again, this is my friend who will help me. And what will I do here? Now tell me, can you find an x? No, you can find many values. X can be 2, x can be negative 2, but what is the requirement of this operator? It requires a unique answer. So this is still not a number. But now I have two cases, very distinct, even from a computational perspective. If you do that floating point arithmetic, 0 by 0 is one way of computing something, 1 by 0 is another way, and minus 1 by 0 is yet another way. So actually there are three ways. So in order to distinguish between these three cases of undefined, they are all undefined, right? We want to call this, actually here the programmers, they love to call it NN, and for infinity they love to call it, so INF, negative INF, IEEE, I hope you are aware of IEEE floating point arithmetic standard. If you want to search it, it's called IEEE 754. It has a precise representation for plus infinity, minus infinity, and not a number. And the purpose is not to claim that they are legitimate numbers. The purpose is just to distinguish between these three ways. But don't think that these are the only three ways to get undefined. I already gave you an example, that's square root of 2. So there are infinitely many ways of getting to undefined. We will not be able to give name to each one of them. So think of this plus infinity, minus infinity, and not a number as just convenient tools. In other cases, we just say undefined.
Sir, pi is number or not? Pi.
If pi, that depends on the type of number. If you have a crystal clear definition of real numbers, right? Real numbers. So real numbers, I'm sure you have heard this thing called, let me try to recall that mathematician. Yeah, I forgot his name, but I hope I can remember the name. But he actually gave a way of filling the real line, right? So normally if you stick to rational numbers, and you all know what rational numbers are, people thought that there is no gap in this real line because you can make numbers smaller and smaller. Yeah? Let's say just pick any two now, do 2 points, right? 0 and 1. So you can fill this line, this interval by as many points as you like by making things smaller and smaller. So, but it turned out that there are still things like I said you x squared is equal to 2. So, what you need in this case is that you cannot construct an example. So, computationally pi for a computational engineer or a numerical computer scientist, pi is not computable. So, they will refuse to call it a number. But if you call a mathematician, they don't care about implementation. What they say, when they cannot construct something, they have another tool for this. They define what we call, you must have heard this, right? Axioms. So there was this one mathematician, I'm still struggling to recall his name. What he did, he gave a super axiom to claim that all the real line can be filled whether you can construct something or not. So by that axiom, pi is a number. But only, now I know there are mathematicians who are more inclined towards computation. Their argument is that if you cannot, even with a Turing machine, right? So they say a Turing machine cannot compute the value of pi even if it is given all the resources and all the available time. It will keep computing, but it will not be able to compute. So, but this is a philosophical difference. The mathematicians say, okay, we don't need to compute it. It is just there, and you have to believe it. So that was a tough question in a way.
My last question, sir. When you define pure algebraic or pure mathematics, doesn't its realm coincide with the metaphoric and metaphysical and all this? Because between 0 and 1, you know, and I know, we can go to beyond limits, even infinity, if we go to infinitesimal small numbers. So we have to have cater and find solution to the engineering problems.
Yes, yes.
So the imaginary value that there are infinite numbers between 0 and 1.
Yeah.
What is the?
I think.
What is my player to have that?
I agree with your point, but I think what if you see, if you try to define real numbers, right? Let's say you want to define real number in this way, right? So there, you guys must have heard. So although the mathematicians cannot have a concrete computation, but they use logic. So if you have a consistent logical condition, so I'll just share with you briefly how they justify the definition of irrational numbers. Pi is one example. What they do is this. And actually there was a guy called, maybe you should write this name, Dedekind. Dedekind did something very, very cool, okay? So he said that, okay, think of this real line and think of all the numbers which you can construct by a Turing machine. And you know what are those numbers? All the rational numbers, yeah? Because you can write a program with a finite number of steps to compute any rational number. So they say, okay, you fill it with those numbers, right? And then Dedekind helped to define irrational numbers. So how he defined it? He defined it in this way. He said, imagine a point here, right? Regardless of whether you can compute that point or not. So he said that, okay, what you do, think of this point as, because this is an infinite line, right? Infinite line. So think of this as a cut. So he called it the Dedekind. Think of it as a cut which divides the real line into two subsets or two partitions, right? So you can imagine this even if you can't compute it. So what will be your representation? Let's call this x, right? So what will be your representation for this part? I think you know the notation, yeah? Right? And let's say we include this in this part, right? And maybe we can do that, right? Right? And then this one will be x. So now you have these two cuts. And let me try to recall what was his next argument. His argument is that now the question whether you include this x in one of them or not will be determined by whether this x is rational or not. Now, whether a number is rational or not is something which you can do computationally. So that is in computer science it's called decidability. Yeah. So you can write a computer program to determine whether a number is rational or not. So if you can do that, you include this, and if you can't do that, you exclude this, right? So here, this case will be, so if x is not rational, I will divide it in this way. So it means that between these two sets, there is a point, there is an object which must exist by logic, even if I cannot compute it, right? So what Dedekind did, he defined irrational numbers in that way. Yeah. So whenever you have these cuts, so if the cut happens to coincide with the rational numbers, and rational numbers are computable or decidable, that is something you already know. But if you cannot prove that it is a rational number, then that number must be a rational number. So you see, it is an indirect way, and I think the reason many mathematicians accepted this definition, even if they cannot compute it, because it doesn't violate any logical rules. Yeah? So by that definition, pi is a real number. Why? Because I can construct this cut, and same goes for that natural number E. Huh? Sorry? No, it doesn't matter whether I accept or not, because I don't matter. What matters is the community. So I would say that an overwhelmingly large community of mathematicians, they accepted it. Computational engineers, they have refused. I know people who believe that pi is just, and you know what they say about pi? They say is that pi is just an ideal object which we can approximate, but it itself doesn't exist as a number. And my friend Faisal, he knows that it is very unfortunate to talk about that guy, Muhammad Atif Khan. He belonged to that community. They don't accept rational numbers as actual numbers. So you know how they define rational numbers? They say these are not numbers, and maybe because I see many of you are applied mathematicians or engineers or computer scientists, you will like this idea. So what they did is this. What they did is something like this. They say, let's say we define to construct pi. Okay? So what will I do? I will start with 3, yeah? 3 is my first approximation, right? The next approximation will be, 3.1. What will be the next approximation? The next? One last, and then I'm. Okay. Before I get to the definition of pi, if I ask you, what is this as an object? A number, yeah? A legitimate number, because it is rational. What is this? A number. Rational number is legitimate by your sense. So they are all numbers. But what is this whole thing as an object? A sequence. It is a sequence, right? It is a sequence. Now, this sequence doesn't end, right? Even if we can't construct it, we know that it is an infinite sequence. Infinite sequence is an accepted object in mathematics. So they define pi as this sequence. Muhammad Atif Khan, yeah? This was his definition of pi. So every now and then you hear news, oh, Google calculated 1 billion digits of pi. And then we hope, those who do not know that pi is not a legitimate object, they think that one day pi will be computed. That one day will never come because by definition it is not computable. Yeah? Yes?
Pi and infinity, they both belong to the same?
Pi and?
Please use them.
Because we have switched the arguments.
No, there is one important difference. There is one important difference. Pi is not special. Pi, even though we cannot prove its existence, but we can prove that it is finite. We can prove that it is a finite number if we accept the number. But infinity is unbounded, right? So infinity in the real line is never reached. But here, you know pi has to be somewhere if you accept this as a number.
When you were writing those notations from minus infinity to x,
Yeah.
and x to, so there was a feeling that maybe infinity is also a number. Similar.
No. That minus infinity only is a shorthand for saying that all the points to the left, all the way down to the left. So when I say minus infinity comma x, it doesn't mean that minus infinity itself is a number. It means start from x, go to the left, and don't stop. So that don't stop is not cool to write. Yeah? So minus infinity is a cool way of writing that don't stop. So in that sense, I think pi को इतनी respect हमें देनी चाहिए कि minus infinity की तरह नहीं है.
How far we are with the execution of this precise way of writing method?
Lean has already done that for you.
So we can execute
So
this?
my next lecture will be on lean.
Interesting.
All these are, I would say most of these, because they are still working on it. It's a very active community. They express most, and you will be very surprised to know that many of the things I wrote, they are written in the good thing about lean is that it accepts Unicode. So C++, Java, Python, they cannot deal with Unicode. They require you, for example, if you want to write Lambda, you have to write Lambda. But Lean and Julia, they both, they allow you to write Lambda like this. And it is, so and similarly you can write this. Yeah. So in that sense, Lean and Julia, they allow you to express your math as you would write it on a piece of paper. And they can then process those equations.
Thank you.
किसी और का क्वेश्चन है?
अच्छा मुझे भी पता चला कि इधर पानी भी पड़ा हुआ है. Exists. So the water exists as a bottle, not as a number. Yeah? Are there any other questions? Thank you.